Hi, welcome to the class. Now we will discuss, like in the previous class we discussed about Rutherford's alpha particle scattering experiment. He gave a wonderful theory, but there were some drawbacks about the theory. And the very first drawback was he said that whenever electrons revolve around the nucleus in the orbits, they basically radiate energy, right? And when they will continuously keep on radiating energy, they will come closer to the nucleus, and when they are very close to the nucleus, they will collide with the nucleus, and as and when they collide with the nucleus, the existence of the matter will come in danger. And we know that matter is quite stable, it doesn't happen like this, right? So that was the drawback of the Rutherford, that was one of the drawback of the Rutherford. And in order to remove this drawback, there was this person, Niels Bohr. He explained the motion of the electron around the orbit, and also like how electrons absorb and radiate energy and when they will do so. So that is the important thing. So Bohr's postulate, so first postulate which he said that electrons revolve around the nucleus in certain permitted orbits, and these permitted orbits are known as stationary orbit, right? So these electrons revolve around the nucleus in certain permitted orbits, and these permitted orbits are known as stationary orbits. And while revolving, when electron revolves in any orbit, then its angular momentum, okay, the angular momentum of the electron, the angular momentum of the electron, L is the representation for angular momentum. The angular momentum of the electron while revolving around the nucleus is equal to, in a particular orbit, it is integral multiple, this is integral multiple of a constant, and that constant is h upon 2 pi. So if you remember, we did in the electrostatics Q is equals to plus minus NE, where this plus minus N was the integer, and we called it quantization of charge. We said that whatever charge will exist in an integral multiple of this smallest possible charge, which was the charge of an electron. Similarly, we are saying that whatever angular momentum of the electron you will find when it is revolving around the nucleus will be integral multiple of a factor which is h upon 2 pi. So for this we said quantization of charge. For this we are calling it quantization of angular momentum of electron while revolving around the nucleus. So this was the first postulate, right? Now about the energy part, Bohr said that this is lower orbit, this is higher orbit. Here is the electron. He said that when electron will jump from the lower orbit to the higher orbit, it will absorb energy. It will take up energy. And how it will take up energy? In the form of photon. And what is the energy of the photon? E is equals to h nu. So it will absorb energy, and it will take the energy of h nu, and it will jump to the higher orbit. Similarly, so it is absorbing energy. When it jumps down from the higher orbit to the lower orbit, it emits out this h nu. So, like Rutherford said that it continuously radiates energy while revolving, that is not the case. It will absorb and radiate energy only when it goes from lower orbit to higher orbit. It will absorb energy, and higher orbit to lower orbit, it will radiate energy. So let us assume that energy here on the higher orbit is E2 and energy here is E1. So obviously this difference in the energy will be equal to E2 minus E1 will be equal to h nu, because when the electron is at h, that is higher orbit, it will have more energy by a factor of h nu, and this is what we call Bohr's frequency condition. This angular momentum is what we call Bohr's quantization condition. You know why? Because the angular momentum is being quantized, and in the second case, from here if you take out the frequency, it will be E2 minus E1 by h, and this is what we call Bohr's frequency condition, right? So this was the Bohr's theory. Now Bohr applied his theory to the simplest atom of all. Now you have to make a guess which atom it could be. The simplest atom of all. So the simplest atom of all is hydrogen atom. So basically he applied his theory to the hydrogen atom. So again, if I draw it here, this is the atom of hydrogen atom, and there is a nucleus inside it. As discussed in the previous class, the charge of the nucleus will be taken as plus Ze. This is the radius r. Here is the electron having a charge e. Of course, this charge will be negative. This is the velocity v, and this is the radius r. What we are trying to do is to find out an expression for the radius r, right? So how do we do that? You know that there is a force of attraction between these two. How much is that force of attraction? That force of attraction is F is equals to 1 upon 4 pi epsilon naught Q1 into Q2 upon R square. Force of attraction will be 1 upon 4 pi epsilon naught ZE square upon R square. This is first equation. Now guys, you know that as this electron is revolving around the nucleus in the spherical path, it cannot revolve on its own. For revolution you need something known as centripetal force, and also that centripetal force cannot be generated on its own. Some force has to generate this centripetal force. So in this case the centripetal force is generated by this electrostatic force of attraction, and therefore that centripetal force would be mv square upon r. So this is the centripetal force. It is generated by this force. So if I equate these two, because since it is generated by this force, this has to be equal to this two. They both has to be equal. R goes off. Guys, I want you to remember this equation. I will be using it later on to find out the kinetic energy. As you could see that kinetic energy is half mv square, and I have already got the value of mv square. So I will just multiply it by half and it will become kinetic energy. So this is an important expression, we will use it later on. But coming back to the expression for radius, from here radius can be taken out as Ze square upon 4 pi epsilon naught mv square, right? This will be the expression for radius. But there is a problem here. The problem is the velocity, that this expression contains velocity. And I do not want to have two unknown constants in a single equation. I want to be specific. I want to find out the details for radius. Therefore, I have to remove it. How do I do that? Using the Bohr's quantization condition. Now, what was Bohr's quantization condition? So, you all should know that the Bohr's quantization condition was mvr is equals to nh upon 2 pi. I will find out the value of v from here, nh upon 2 pi mr, and I will use this value of v here. So I will put the value of v and square it because it is v square. So guys, I am leaving that part up to you. I will just write the final expression, and the final expression will be r is equals to n square. Remember that n is the orbit, nth orbit. It could be one first orbit, second orbit, third orbit. N square h square epsilon naught upon pi m z e square. Now look here, z is the atomic number. So since we are talking about the hydrogen atom, it has to be 1. N, hydrogen only has one orbit, so this n will be 1. H is a constant, epsilon naught is a constant, pi is a constant, m is a constant, e is a constant. Everything is a constant. So if I put the value of all these things, first for hydrogen atom, I am writing like this: for hydrogen atom, n is equals to 1, z is equals to 1, rest everything is constant. If I put the values, you know the value. This r is coming out to be radius of the hydrogen atom is coming out to be 0.53 angstrom. 0.53 angstrom. So this is the radius for hydrogen atom, right? One important result more I can find out from here. As you could see, rest each and everything is constant, right? So I could establish that if everything is constant, I will remove those constants and bring in proportionality, and I will say that the radius of the nth orbit is directly proportional to n square, because everything else is constant. If I give the value of z as to be 1, 2, 3, whatever, you could see that the radius of the nth orbit is directly proportional to n square, and this is an important relation, right? And I'll just show you one question which comes in your exam from this part, and I hope this part is clear. These are the two important conclusions which we did from this expression. One is for the hydrogen atom, that the radius of the hydrogen atom is to be 0.53 angstrom. If you apply it for some other atom, you can change the value of z, and also about the orbit also, like which orbit you want to find out. And this is an important relation which we have established from this. So I hope this part is clear. Let me just do that question with you, which I am telling you is based on this part. So the question which is, like, I'll read out the question first. The radius of the first orbit of the electron of a hydrogen atom. So radius of the first orbit of the electron of the hydrogen atom is given to be 5.3 into 10 to the power minus 11 meter. Now you will say, sir, we told that 0.53 angstrom. So guys, this I'll just do it here. R is equals to 0.53 angstrom now. So R is equals to 0.53 into 10 to the power minus 10 meter. So it can be written as 5.3 into 10 to the power minus 11 meter. This is what is given, right? They want you to calculate what is the radius of its second orbit. So R2 I have to find out, which I don't know. Second orbit. Second orbit they are saying, right? I will use this Rn proportional to n square. I'll remove the proportionality, put the constant, and I'll make this as a general equation for myself. Right? Now if I put n is equals to 1 here, k, of course 1 plus square will come. This value is given to me. That becomes 5.1, 10 to the power minus 11 is equals to k into 1 plus square negative. So you got the value of k. So you got the value of k. Now, to find out it for the second orbit. Similarly, we will do R2 is equals to k 2 ka square, because this n will become 2. R2 you do not know, value of k you know, 5.3 into 10 to the power minus 11 into 4. So R2 will come to be 21.2 into 10 to the power minus 11. 21.2 into 10 to the power minus 11 meter. This is how it is calculated. I hope you understood this part as well. So that was the question. Now in this question one more variation might come, and the variation could be, instead of asking about the second orbit, they will ask you about the second excited state. Instead of asking second orbit, they will ask you second excited state. Now guys, most of the students gets confused because they think that second excited state means n is equals to 2. No. Second excited state means that if we have, here is the ground state, this is the ground state. So this is n is equals to 1, ground state. First excited state is n is equals to 2. So n is equals to 2 is what we call first excited state. And then n is equals to 3 will be second excited state. So second excited state is not n is equals to 2, but is n is equals to 3. Similarly, third excited state is not n is equals to 3, but n is equals to 4. I hope you understood this. We shall continue the discussion. Thank you so much.